So what's it take to turn an amp that sucks into an amp that's pretty awesome? It seems like in some cases it might be pretty easy. Welcome to Lancaster Hi-Fi. I'm Stephen Lancaster. I've been doing a series of videos about this Altec Quartet, or Model 344A, integrated monophonic amplifier. I have finished it and started doing some testing. My initial testing was like, dang, this thing kind of sucks. I mean, it was okay below 1 kilohertz, but above that, it started distorting, slewing distortion, which I've talked about before. So the other night I was doing some measurements of maximum undistorted power. And I was being pretty persnickety about what I considered undistorted. So that if I essentially detected any distortion to the sine wave, I would back off until it was undistorted. And that included slewing distortion. The black is the Altec amp under test. For reference, and because I'm simply reusing another spreadsheet, red is the Beaver Valley amp. As you would expect, max undistorted power rises, or let's say drops off pretty steeply at very low frequencies. Then it's pretty flat, but over 1 kilohertz, it already starts to drop. It's a little jaggedy here, the way it's plotted, and I would attribute that mainly to the somewhat subjective determination of whether it's distorted or not. But the point is that it falls off pretty dramatically for anything over 2 kilohertz, which just shouldn't be. That's kind of lame. That's super lame. When I've talked about slewing distortion before, I've said that it is typically not an easy problem to solve and may require redesigning the amplifier. May even require using different tubes on, say, the input stage of the power amp. So when I was getting quite a bit of slewing distortion on this amp, I was like, dang, it's using a 6CG7 on the input and phase splitter stages, and that's a pretty awesome tube. But maybe it just wasn't biased well. Maybe I needed to address that biasing. And I'm trying to figure out, well, maybe I'm running the tubes too cool. Maybe if I crank up the current, I can get better response. But this kind of distortion is probably due to the input stage of the power amp. Let's go to the schematic here. So we're using 6CG7s, which are similar to 6SN7s. But we're running it at pretty low current, and the input stage is running at lower current than the phase splitter, and I think that might be the problem. But the problem with cranking up anything, if I crank up the bias current on the output tubes, if I increase the current draw by this tube, can the power transformer handle that? I don't know. And I actually looked into other amps that use either a 6CG7 or 6SN7s. Yeah, they were typically using more current on the input stage than this one is. It's like, well, okay, I could change that. But I did put in this adjustable bias for the fixed or grid bias on the output stage. So if I'm going to make grid bias adjustable, I need to have a way to detect the results of the adjustment. So that's what this is here. You can't really see it very well from this side, but I've got a terminal. Basically, it's a banana plug receptacle, but it's useful for any sort of voltage probe. And then that's simply attached to the grid on one of the output tubes. I can detect on the top side with that and adjust here. I'm not putting in a ground terminal because you can just use the chassis. I wasn't real sure what to bias those tubes at initially. I knew what the bias supply voltage was supposed to be according to the schematic, but it didn't specify what the bias current was supposed to be, and this amp's pretty obscure. I couldn't find anybody online telling me what the bias current was supposed to be. And, you know, that makes sense if people who've restored these in the past have kept the bias supply as it was designed initially. But since I put in an adjustment pot, I figured, well, let's check it out. It's like, okay, well, you know, the bias current at somewhere around minus 16 volts on the grid is pretty low compared to the way people bias either EL84s or 7189s, which are basically the same thing. The bias current was pretty low compared to how people usually bias those tubes, at least nowadays. For example, my Beaver Valley amp biases those tubes at like over 12 watts of plate dissipation. And the way they were biased, the way I initially had it, it was more like 6.5 watts plate dissipation. So I figured, well, let me crank it up. Maybe not to 12 watts of plate dissipation, but maybe 90% of that or 85% of that or something like that. I'd really rather not get into redesigning this amp. According to my calculations, about 90% of maximum quiescent plate dissipation should be at about 25 milliamps per tube here, which means I should crank this up so that the voltage that I read is 250 millivolts. There we go. Overshoots, of course. I'm going to wait for it to come back down to something like 420 volts, which is what I've been seeing so far. And what we will probably see is if and when I crank up the bias current, that voltage should drop. And I'll need to account for that in my calculations of how much I crank up the bias current. I crank up the bias current, the voltage will drop, which will affect the calculation of how much plate dissipation is going on. Lower plate voltage means lower plate dissipation, so these things will seesaw a bit. Okay, so I had previously set it to 15 milliamps or 150 millivolts. And so what I want to try to do is crank that up to about 250 millivolts. All right, let's see what the plate voltage is now. Okay, as expected, the plate voltage has dropped substantially at 20 volts lower than from my calculation. I could run it up higher. Just try cranking it up another couple of milliamps. We're 27 milliamps now, and we've not dropped the voltage very much. Max plate dissipation is 12 watts, and I'm just going to assume that all of the current is through the plate. Some will actually be through the screen grid. 400 volts times 27 milliamps is 10.8 watts. So I'm going to try cranking this up just a little bit because I can go as high as 12 watts. And the Beaver Valley runs right at 12 watts, maybe even a little over. So there's another milliamp to 28 milliamps, still at about 400 or 399. I'll do the calculation based on 400. So 28 milliamps is 11.2. And I think I may just stop right there. I'm curious to see what the bias supply actually is. Minus 12 volts. Different data sheets will tell you slightly different things about how much bias current an EL84 or 7189 can take. I think sort of the design center maximum is like 12 watts, but the actual maximum is like 13.6 watts of plate dissipation. What that means is that the voltage drop across the tube times the current through the plate. That's the plate dissipation power. I'm not actually measuring plate dissipation when I do measure. I'm actually measuring the current through the cathode, which is plate dissipation plus screen grid dissipation. But most of the dissipation, most of the power is through the plate. Anyway, all right. So I cranked it up to, something like 90% of that 12 watts. And damned if a lot of that distortion didn't just disappear. And all of a sudden, it's a pretty awesome amp. I mean, at least up to 10 kilohertz, and it starts to drop off above 10 kilohertz. But, distorting above 10 kilohertz is more or less acceptable. Distorting below 10 kilohertz, completely unacceptable. So, yeah, it went from an amp that was by no means acceptable to one that's fine, that's pretty awesome. Well, I haven't actually listened to it, though, to determine that that's true. I mean, I've done the scope stuff, and I'll show you that. So I'm feeding it with 1 kilohertz signal now. So there's 1 watt. All right, starting to see the distortion here, and there's clipping, and the crossover distortion. That's 12.6. I'd call that still a bit distorted. 12.5 looks pretty good. 12.4 is better. So 19 watts. 19.2 to be precise. Be interesting to see if this might have somehow improved the high frequency response. I was finding that 5 kilohertz, it had dropped off below 10 watts undistorted. So I'll turn down my main volume a bit and change the input frequency to 5 kilohertz. And let's see what we can do now. Let's see what it looks like at full power, at 12.4 volts. And not bad. I don't know if I'd call that undistorted, but it's not bad at all. I think I may have effectively solved this amp's problem. Isn't that cool? Let's bump it up to 10 kilohertz. Wow. You can detect a little bit of slewing, but it's dramatically improved. So here's what the frequency response looks like now with the bias current set to 28 milliamps, and it's dramatically better. It still does roll off over, it's starting to roll off here, 12.5 kilohertz. By 16, it's down quite a bit. But I would suspect that people in my age group can't hear that high, and that this bit of roll off at 12.5 is going to generally be insignificant. I mean, we're still talking 15 watts, so very nice. Now, the transformer's pretty hot, and that's not unusual in my experience to have transformers on tube amps running hot. But, it's something to keep in mind. I am going to refrain from turning the bias current up any higher. The other thing to note is that, again, I'm being very picky about the no distortion thing. It's going to tolerate being cranked up to relatively high power at those upper frequencies. It's just going to be a bit distorted. But I'm also going to do some listening tests because I want to know, can I tell the difference in the sound? Now, it is a monophonic amplifier, and I haven't finished the other amp yet, so I've had to choose some mono recordings, CDs. So we're going to listen to some jazz. Well, you can see it's actually been biased at 30 milliamps, which should be fine. I'm going to turn it down to about half of what it is now, to 15 milliamps or 150 millivolts on the meter. Okay, there we go. I'm gonna give it a little time to stabilize. I'm gonna call it good. I mean, they both sounded good. I'm not sure I could point to a difference. You know, maybe it would help to do some other kinds of music. I'm not hearing a marked difference. I'm a little surprised. But, on the other hand, maybe I'm not so surprised because, you know, I haven't totally cranked it. Although it's kind of loud. I didn't want to listen to it any louder. Yeah, I mean, once I get the other one done, I'll probably do some more tests with both channels, you know, some actual stereo music. It's a little bit tricky to test for music with just the mono. Well, I hope you enjoyed that video and got something out of it. And if you did, I hope you'll give it a thumbs up, a like, subscribe to the channel, leave a comment, share the video, all that algorithm stuff. Mostly, I hope you'll tune in again. And if you do, I'll talk to you later. Cheers. So testing proceeds in stages. We don't just put in all the tubes all at once, plug it into the mains power, and let her rip. We start with the very modest step of plugging it in with no tubes to the dim bulb tester and turning it on and making sure there's no craziness going on at that stage. Okay, plugged in. I don't expect it to draw any current. And so I don't expect the bulb to light up at all. And it didn't. So that's good. Turn it back off. The next thing is to put in all of the tubes except for the rectifier. Plug it in through the dim bulb tester to make sure there are no shorts in the heater wiring. And then plug it into mains power and make sure all the tubes that are plugged in, that all their heaters light up. It's not wanting to go all the way in on one side. I'm figuring that some solder got wicked up into the friggin' thingy. Okay, that was the issue, and my remedy was successful, which essentially amounted to pushing the tube in while heating the pin, and then also making sure that the tube would come back out, because wouldn't want to actually solder the pin into the socket. That's sort of the risk there. So now I can plug into the dim bulb tester again. Here. So I'm seeing glow here, here, and here. And here. Okay, it's glowing a little bit. Go straight into mains with this configuration. See what we see again. Okay, I have glowage all around. That's good. But the next step will be to take all of these tubes out, plug in the rectifier tube, and check voltages on the underside without any tubes attached. You can't get a very accurate read on the voltages that way because the correct voltages rely on the tubes drawing their power. In general, the high voltage should be too high without any of the other tubes connected. Let's do this. First, I'm going to plug into the dim bulb tester. Okay, the bulb is very dim. Let's see, what do I have? Okay, yes. Rectifier tube is glowing. Okay, interesting. Very quickly, the bulb came on kind of dim and then went very, very dim. And then as this warms up, it went a bit bright again. And now it's back to dimmer, but not as dim as it had been. Turn it off again. Interesting. So the neon light is just still lit, even though I turned it off. The neon lights are getting their power straight off of the high voltage. The high voltage is staying high, which is kind of interesting and a little scary. I've decided to measure voltages with just the rectifier, without any other tubes, and through the dim bulb tester. Even if that's just a little bit safer than without the dim bulb tester, it's important to review and emphasize safety procedures. First of all, I will use one hand, which is a bit tricky when reaching in with probes. On the subject of probes, you don't want to stick any more metal in there than you have to. Now, I had already done this, put shrink tubing to cover some of the metal on the probes, but I just put on new shrink tubing for this purpose. You will note also that I have put shrink tubing on my tweezers. Not that I'm going to be reaching into an amplifier that's on with tweezers, but just in general, I like having that extra bit of safety. So, first thing, one hand stays in the lap. I'm just using the one. And the other thing is, since I'm going to be trying to just measure voltages, I can just hook this one up to ground. I'm just going to hook this one up to the chassis. Checking continuity. Alrighty. I'll be checking the negative bias supply, which comes off of this pot here, goes to here, over to here. There's my primary high voltage. There's the screen supply, which should be just a little bit lower. It might not actually be any lower because it's drawing no current, right? You drop voltage across a resistor if you're also drawing current. So I might expect to find that my secondary voltages, so for example, here's the screen supply, then we drop from high voltage over here to this supply, which goes to the driver tube. From there, drop over to here, where that's the supply to this tube. From there, drop over to here, underneath this capacitor, supply power to this tube. Because I'm not going to be drawing any current, these voltages will be higher than they would be if I were drawing current. I think I've got sufficiently high voltage rated capacitors. In other words, these are all 450 rated, and then the big one that's mounted on the top of the chassis is rated at 600. So especially with the dim bulb tester, I should be fine. But ordinarily I might want to be mindful, if I weren't using the dim bulb tester especially, I might expect my primary high voltage to go quite a bit over 400 volts. And then since none of these others are drawing any current, that I might need to watch out about surpassing the voltage rating of these capacitors. So all that said, again, one hand stays in my lap. Of course, I'm only ever going to reach in for demonstration and or manipulation with a non-conductive chopstick, but actually I'm going to stick these tools out of reach, out of easy reach anyway. All right, here's the power switch. So I'm actually going to use my left hand, but I'm putting my right hand in my lap. And I can see what you can't see, that the rectifier tube is glowing. So first I want to check that high voltage. 420. That's pretty high. But I got to remember that I'm not drawing any current. So I expect all of these voltages to be pretty much the same. It's a little lower. Must be something to draw some current there then. I don't know what. Can't remember what right offhand. And that one's also a little bit lower. Alright, now what should be drawing the usual amount of current actually is the bias supply. Okay, minus 18. And I think then I'm going to turn that down. So let me first see whether the directionality of turning it is correct. Okay, that puts it at a larger magnitude of negative voltage, which actually is what you'd want. It's a little counterintuitive, but putting a more negative voltage on the grid of the output tubes actually makes the current lower. The closer you get to zero, the more current that tube is going to draw, because its job is to inhibit current flow from the cathode to the anode. And so you actually stick a negative voltage on there, and that tends to repel the electrons that might otherwise go to the plate. Hooked up the dummy load because you always want to have a dummy load attached when you turn on an amp. There may be cases where you don't need to have a dummy load attached, but unless instructions are telling you otherwise, have some kind of load attached to your tube amp before you turn it on. Okay, I've got all the tubes in. I am on the dim bulb tester, so my voltages should be lower than, well, they'll be lower than they would be otherwise when I'm connected directly to mains power. So now it does get quite bright initially, and then it dims. With all those tubes in, it won't get exceptionally dim, and I should see it brighten a bit once the heaters warm things up. So the heaters are always going to draw a relatively large amount of current compared to any kind of solid state amp. So the bulb never gets super dim with all the tubes in. But I would expect it to brighten up a bit as the tubes warm up and the tubes start drawing current. As we expected, it's quite a bit lower than it would be plugged into mains. I should see something like 395 volts on this if I were plugged into mains power. It's all looking good. Time to plug into mains voltage without the dim bulb tester. So we do expect it to take a little bit of time because things have to warm up, but yeah, bang, now we're at high voltage and getting higher. And it'll rise quite a bit higher than it will eventually stabilize at. And this is why you don't want to use, for example, on this amp, a capacitor that's only rated for 400 volts. It'll probably come down when I turn up the current with the bias supply. Let's see what our bias voltage is set at. Okay, minus 30. It's supposed to be set to minus 17. The thing is, I don't know the spec for what current these tubes are supposed to draw. So I'm connecting my probe through the jumper to the bias supply, and I'm going to turn it up. Well, actually, we'll be increasing the voltage from minus 30. I should get up to something like minus 17. And that will also increase the amount of current going through my output tubes. While I'm doing this, I expect that the high voltage is going down. I'm purposefully going slowly here. Now, one thing I want to show you is the effect of that particular voltage setting on the current being drawn by the output tubes, which are over here. Remember, I had attached 10 ohm resistors between cathode and ground, about 290 millivolts. Current is 290 millivolts divided by 10, so 29 milliamps. Now I'm going to turn down to make more negative this voltage, just an arbitrary amount. We'll measure what that voltage is. Okay, so it had been minus 17, now it's minus 22, and now the voltage across the 10 ohm should be much lower, so now it's 100 millivolts, that is 10 milliamps. I want to check and see what those heaters are, what voltage the heaters are running at. Oh, good, 6.3 volts. Right on spec. So now the thing is to turn this back off, put in the 7189s before I burn out these friggin' EL84s. I have here a set of 4 matched new manufacturer Tungsol 7189 tubes. Plate current 36, which I'm assuming means 36 milliamps. GM 9700. For all of them. So these will be better suited to high voltage. Even so, the datasheet for 7189s says that your max plate voltage should be 400 volts. So these will be running hot, but running hot in terms of voltage doesn't necessarily mean I need to run them hot in terms of plate current. Okay, that's what the schematic says we should be at. Voltage at the cathode is 105. Briefly, how do we set bias current on this Altec 344A now that I've modified it to have an adjustable bias current? Okay, we've got a probe point here. The other probe is simply clipped to the chassis for ground. So I just rest that in there, and I'm hooked up to a digital voltmeter to tell me the millivolts. Now I am looking at the voltage across a 10 ohm resistor from 10 ohms between ground and the cathode. So in order to get milliamps, I just divide millivolts by 10. So 280 millivolts is 28 milliamps. How do I adjust it? I adjust it with this knob over here. That's where the hum pot used to be. I've changed out the hum pot for one of these 10-turn 50K pots. 50K is a lot, but it's a good pot, and we got 10 turns to work with. And so turning that knob clockwise, that is turning it up, will turn up the milliamps. Turning it counterclockwise will turn down the milliamps. So let's see if I can get these both in shot. If I turn it down, millivolts and hence milliamps goes down. If I turn it up, again, millivolts and milliamps go up. And I want to let it warm up for a long time and stabilize. And, check back in with it to make sure it's stable at about 280 millivolts. A little more, a little less, no big deal. But do note that the transformer is running pretty hot at this amperage. So probably don't want to go too much higher. Anyway, let's fine adjust this again to 280. And again, we can leave it for a while to make sure it's stable at that.